This is the second preliminary lecture for PH3203, Advanced Quantum Mechanics. In these preliminary lectures, we are recapitulating some of the topics that you have already covered in earlier courses, but we are going to take a look at the mathematical details a bit beyond perhaps what was covered in those courses. In the first lecture, we had seen in detail how to solve the Schrodinger equation, the time-independent Schrodinger equation for the harmonic oscillator. And today, what we will do is, after a very quick summary of what we did in the last lecture, we will delve in the mathematical details of the new kinds of functions that we had obtained there, namely the Hermite polynomials. We will also try to take a look at these results in a somewhat more general setting, so that once we have the general results in our hands, we can try to apply them not only for the Hermite equation but for other differential equations which will arise while we go through our work. First, a very quick summary of what we studied in the last lecture. What you can see on the screen right now, of course, is the time-independent Schrodinger equation for the harmonic oscillator, namely for a potential V of x, which is half m omega square x square. Now, in the last lecture, what we first learned is that we would have to declutter this equation by changing variables, and with this change of variables, x defined as root over h cross by m omega z, and lambda just being a shorthand for twice e by h cross omega, this differential equation became a rather uncluttered version. The same equation, it just looks neater now. Psi double prime plus lambda minus z square psi equals 0. What we see next is that by looking at the asymptotic behavior of this equation, we decided that this equation has two possible asymptotic behaviors. It can behave like e to the plus z square by 2 when z becomes very large, or like e to the minus z square by 2. And because we want a solution which dies out as z goes to plus minus infinity, we decided to take e to the minus z square by 2 times a function of z for psi of z and rewrite this to find an equation for f of z. This equation turned out to be the Hermite equation, f double prime minus 2z f prime plus lambda minus 1 f equals 0. We solve this using the power series method. After all, z equal to 0 is a perfectly nice regular point for this equation, so standard power series centered at z equal to 0 will work. Using the power series method, we found that unless we chose lambda, this parameter, to be 2n plus 1, where n is an integer, non-negative integer, this series for f of z is going to diverge as z goes to plus minus infinity. Diverge much more strongly than the e to the minus z square by 2 factor that we have put in along with it. So in order to have a wave function psi which is well behaved for very large values of z, we must choose only certain values of lambda, namely odd integers, and as a consequence, the energy turns out to have only certain possible values, m plus half times h cross omega. Now, once we choose this particular lambda, the recursion relation between the coefficients c nu turned out to be this. C nu plus 2 is twice nu minus n by nu plus 1 into nu plus 2 times c nu. This shows that if n is a non-negative integer, then when nu is equal to n, the right hand side vanishes. So cn may not be 0, but cn plus 2 will be, and the series truncates. Now, let us take a look at what happens to the function f of z for some choices of values of n. Remember, n is the largest power or largest non-vanishing power in this series now. So, of course, the series, instead of being an infinite series, you have a polynomial. and n is just the degree of the polynomial. So by choosing different values of n, we will get polynomials of different degree. So let's see what kind of polynomials do I get. The simplest choice, if you take n equal to 0, then C0 can be non-zero, but C2 will have to be 0. By the way, if you choose n equal to 0, that means that the even series will truncate, and have only one term, so f of z is just C0. However, in this case, the odd series will not truncate and would have diverged. So in order to get a finite well-behaved wave function, we will have to insist that C1 is 0 in this case. So we end up with this particular polynomial, which is just a constant. Now, the polynomials which satisfy this equation, given lambda is twice n plus 1, which means this term is simply twice n, are called the Hermite polynomials. Of course, this equation being linear, if a particular polynomial satisfies this, then any multiple of that polynomial also satisfies this, which is the reason why the overall constant C0 in this case, C1 in the next case, will remain undetermined. So we can choose C0, C1 to have specific values, and once we make specific choices, we will get what are called the Hermite polynomials. Let me remind you once again, this is something which we did say near the end of the last class, that the Hermite polynomials that we are using are what are called the Physicist Hermite polynomials. Mathematicians use a slightly different definition, especially people who work in statistics use a slightly different definition. The definition is equivalent to this one, but there's a matter of rescaling and so on. But right now, for n equal to 0, we see that our polynomial solution has to be just a constant, and specifically for the Hermite polynomial of order 0, we choose this constant to be 1. So h0z is just 1. Well, for n equal to 1, again C3 will vanish if n is 1, and you put in nu equal to 1 here, you see C3 is 0. That means the series has only one term, which is C1z. So h1z is simply chosen to be, could have been chosen to be z, but it's actually chosen to be 2z. The reason why C1 is chosen to be 2 will be clear soon once the pattern emerges. Well, for n equals 2, you have to work a bit harder, because for n equals 2, C2 will turn out to be 2 into 0 minus 2 by 0 plus 1 into 0 plus 2 times C0. That is, I'm just using this formula for nu equal to 0 here. So C2 comes out to be minus 2 C0. C4 is easy to see, will vanish. Of course, that's what n equal to 2 really means. C2 is the last term you get. And once again, C1 has to be put equal to 0 to get a finite solution. So the polynomial solution for this particular value of n just turns out to be constant C0 into 1 minus 2z square. This 2 is, of course, the same as this 2. Now, h2z, of course, is a polynomial of degree 2, which satisfies the Hermite equation for specifically n equals 2, has to be a multiple of this, and it is chosen to be 4z square minus 2. That means C0 for this is actually chosen to be minus 2. Again, why this choice? I hope you will see soon after we take a look at a few more examples. Well, n equals 3, it's easy to see that C3 will turn out to be a multiple of C1, namely minus 2/3 C1. C5 will vanish. So f of z will simply be C1 times z minus 2/3. That's, of course, C3 here, 2/3 C1. That's the minus 2/3 C1. So z minus 2/3 z cube. And once again, for a specific choice, in fact, for the choice minus 12 for C1, we end up with h3, which is 8z cube minus 12z. So we can go on and calculate a bit more. N equals 4, bit more work. C2 comes out to be in terms of C0. C4 comes out in terms of C2 from the recursion relation, but since C2 is known in terms of C0, you then work it out in terms of C0. So ultimately you end up with C2 equals minus 4 C0 and C4 equals 4/3 C0. And when you plug them in, the polynomial works out to be C0 times 1 minus 4z square plus 4/3 z to the 4. And by choosing C0 equals 12, we end up with the Hermite polynomial of degree 4, 16z to the 4 minus 48z square plus 12. Now, in case you have missed the pattern, let me just go back and show you that H0z is 1, H1z is 2z, H2z is 4z square minus 2, H3z is 8z cube minus 12z, H4z is 16z to the 4 minus 48z square plus 12. I'm pretty sure by now you have spotted the pattern here, or the pattern which dictates what value to choose for C0 or C1. Notice that the highest power of z is of course n for a particular value of n, and the coefficient of that power happens to be 2 to the power n. So that is what dictates our choice of the coefficient C0 or C1 in this case. You could of course use these recursion relations, the relation between C nu plus 2 and C nu, to work out the polynomials for any value of n. It will take more work, of course, to find out higher and higher order polynomials. However, there is another way of writing down these polynomials which make life a bit easier. Well, not so much for finding out the polynomials. That takes roughly the same amount of work in both methods, but primarily for working out various mathematical properties of these Hermite polynomials. In fact, there are two different mathematical things which come in very handy. One of them is the so-called Rodricks Formula, and the other one is the so-called generating function. We are going to take a look at both of these one after the other. Let's start with the Rotrix Formula. Rodricks Formula is actually a generalized name for a class of formulae which gives us various kinds of polynomials, and there's a reason why some very different kinds of polynomials can actually be expressed in terms of the Rodrigues formula. We will explore the commonality later on, but right now let's talk about the Rodrigues formula for the Hermite polynomials. For the Hermite polynomials, the Rodrigues formula happens to be given by this. The nth order Hermite polynomial Hn of z is simply what you get if you differentiate the function e to the minus z square n times with respect to z, then multiply this by e to the z square and put in a factor of minus 1 to the power n. Now this doesn't really look too much like a polynomial at first glance, but if you think about it a bit, each time you differentiate e to the minus z square, you're essentially going to bring down an extra factor of minus 2z from the exponential. Of course, you will also have to differentiate any factors which are already there. So you will end up with e to the minus z square times the polynomial by means of the differentiation. In fact, if you differentiate this n times, it's easy to see that you are going to end up with an nth order polynomial times e to the minus z square, simply because every differentiation brings down an extra factor of minus 2z. So when you are multiplying that result by e to the z square, you cancel out the e to the minus z square and you end up with a polynomial. In fact, it's pretty easy to argue here, why will the coefficient of the highest power or the nth power of z turn out to be 2 to the power n if you choose this definition for h and z? Now, there's another way, a different way of writing down this h and z, which is 2z minus ddz raised to the power n acting on 1. I will let you worry about why this expression actually is equivalent to the expression on the top. It's really rather easy to work out, but let's leave that as an exercise. By the way, I've kept on saying that there's a mathematician's version of Hermite polynomials. In fact, the mathematician's version is very similar, except that instead of e to the z square here, you have e to the z square by 2. You still do n derivatives of e to the minus z square by 2, and the mathematician's version is written he. So henz and hnz are both nth order polynomials, but there is a small difference between them. In fact, you can easily show that this mathematician's version of the Hermite polynomial is related to the physicist version by this expression. We will be using the physicist version exclusively in these lectures. I mentioned the mathematician's version to you simply because if you read a mathematical textbook to find out properties which you are searching for, you may get into trouble if you are confused about which particular version of the Hermite polynomials you are actually using. Let us now see how the Rodricks formula, this particular one, manages to give us the known h and z's for at least some small values of n. H0z is very easy. All you have to do is use this formula for n equals 0. Of course, n equals 0 here means you don't differentiate at all, which means e to the minus z square stays as it is, and that gets cancelled by e to the z square. Minus 1 to the 0 of course is 1, so h0z turns out to be trivially equal to 1. What about h1z? Well, h1z means you're going to differentiate e to the minus z square once. So h1z, simply if you look at this, you're differentiating e to the minus z square once. That gives you minus 2z e to the minus z square. And when you multiply that by the minus 1 which you get from minus 1 to the 1 and e to the z square, the exponentials cancel out and you're left with plus 2z. This was our definition for h1z before. What about h2z? Well, you just have to do two derivatives. One derivative we have already done in the last case. That means you have to differentiate minus 2z e to the minus z square once more. But if you do that, of course the minus 1 whole square is just plus 1, so I have not written that here. When you differentiate this thing, you get another minus 2z from this differentiation, that gives you 4z square. A minus 2 comes from differentiating this term, so it's 4z square minus 2 times e to the minus z square. And there's an e to the z square here. Once again, they cancel and you end up with 4z square minus 2. You can of course keep on continuing on and on to find out h3, h4, etc. using the same technique. However, as we have said, the real usage of Rodricks formula is not to really find out the polynomials. It's more to deriving various important relationships between the polynomials. So let me just illustrate that by showing you how to derive a rather important result called a recursion formula. It's one of the recursion formulas that we will find. So in order to do that, we'll start with hn plus 1. So hn plus 1, z is just from the formula, is just minus 1 raised to the n plus 1 e to the z square, n plus 1th derivative of e to the minus z square. Of course, the n plus 1th derivative is nothing but the first derivative of the nth derivative. Right? But the nth derivative of e to the minus z square is related to h and z. So we just use that now. We just rewrite the bracket in such a way. This is the ddz. All I've done is taken this bracket and rewritten it here by throwing in an extra factor of e to the minus z square and e to the plus z square and bringing the minus 1 to the n inside. Of course, that leaves an extra minus sign outside. Why have I done that? We have done that basically because once you do this, this part is exactly h and z. So what we end up with is this result, that hn plus 1z is minus e to the z square times the derivative of e to the minus z square times h and z. Now we can differentiate this very easily using the standard method for product of functions. So e to the minus z square times the derivative of h and z minus 2z, which comes from the differentiation of e to the minus z square, e to the minus z square, h and z. And once you multiply through by e to the z square, all these e to the minus z squares cancel, and you are left with this very important result, that hn plus 1z is given by this thing. So hn plus 1z is related to h and z and the derivative of h and z. So if you know the nth order polynomial, you can use this to find out the n plus 1th order pretty easily. So this is what the relationship looks like, and is one of the recursion relations which allow you to calculate the next polynomial from the previous ones. Here all you need is the nth and the derivative of the nth to find out hn plus 1. As we will soon see, there are other recursion relations that we can derive, and some of them are more useful than this one. We can derive many more results using the Rodrix formula, but now it is perhaps time to introduce you to the other major tool that we will have at our disposal, that of the generating function. Now, just like we pulled the Rodrix formula essentially out of a hat without an explanation as to how it came about, we will do the same thing with the generating function for the time being. We will start by just considering this function 2tz minus t square. Now this of course is a function of two variables, t and z, and you can expand this out using the standard formula for the exponential. 1 plus 2tz minus t square plus 1 by 2 factorial 2tz minus t square whole square plus higher and higher order terms. Now, what we will do next is we will collect different powers of t. That is, essentially treat this as a function of t with z just as a parameter. Of course, the first term is the t to the 0 term, something which is independent of t. Now, it's also very easy to see that from each of these brackets, from this bracket, the lowest power of t that you are going to get is 2t. From this one, you're going to get t square. From the next one, you're going to get t cube, and so on. So it's very easy to see that up to first power of t, there's only one term, which is 2z, can be treated as a coefficient, times t. What about the quadratic power? Well, you will get a quadratic power from here by squaring this, which is of course 4z square by 2 factorial. That's 2z square minus 1 times t square plus, well, higher order terms. I cannot really write down the t cube term correctly right now because the term which I did not write here will contribute to the order t cube. Of course, I could include this and then correctly write out the t cube term and so on. But you should be able to notice a connection between this and the Hermite polynomials. 1, of course, is nothing but h0z. 2z, if you remember, is nothing but our h1z times t. The coefficient of t square here, well, that's not h2z. h2z is really 4z square minus 2, but this is really h2z by 2. If you wrote down the next term by taking into account the next term in the series, you would find that the quotient of t cube is h3z by 6. And this actually generalizes to all powers of t. It turns out that this function happens to be t to the n times the coefficient. The coefficient just happens to be the nth Hermite polynomial divided by n factorial. N going from 0 to infinity. Of course, this is h0z by 0 factorial, h1z by 1 factorial, h2z by 2 factorial. The 6 really is 3 factorial and so on. So basically, if you treat this function of t and z as a power series in t, then the coefficients up to a factor of n factorial turn out to be the Hermite polynomials themselves. Now this happens to be very useful, as we will soon see in various applications. I will not blame you though if you were to feel a bit uneasy at this stage. After all, this particular function, e to the 2tz minus t square, was just picked out of the blue without any explanation as to where this particular function came from. What I will do now is to show you how you can derive this particular generating function starting from the Rodricks formula. Of course, you might still object that the Rodricks formula itself was sort of picked out of the blue. What we will do is we will then show how the generating function actually leads you to a proof that these h's do satisfy the differential equation, namely the Hermite differential equation, for a particular n. And this should sort of put your mind at ease, at least to the extent that we are getting the correct Hn by using the generating function, which in turn came from the Rodricks formula. So at least it should convince you that the Rodricks formula is right. Later on, we are going to show you how to derive the Rodricks formula starting from the differential equation itself. That's a bit more advanced, but it's actually a very useful thing to know, especially because you will meet similar equations, which are all, by the way, called Rodricks formulas or formulae, for various different important differential equations that you will need to be familiar with in order to be conversant with various calculations in quantum mechanics. First, however, let me show you how to derive the generating function starting from the Rodricks formula, which is simply this. Now, in order to simplify our calculations next, what we do is we define e to the minus z square as a function, or we just label this as a function capital F of z. Now, what the Rodrigues formula really tells me is that h and z is essentially related to the nth derivative of this function capital F of z. Or in other words, we can simply rewrite this in this form, that the nth derivative of the function z for any arbitrary integer n is given by minus 1 to the n times e to the minus z square times the nth Hermite polynomial. Now, if I know all the derivatives of a function, as apparently I do here, at least in terms of this h and z's, then I can simply use this information to write down the Taylor series expansion around the point z. So in other words, I can find out an expression for fn of this function f at z minus t. This is simply the Taylor series expansion of the function z minus t around the point z. The nth derivative goes here. And then you of course multiply it by minus t, which is the change in z raised to the power n by n factorial, and sum up over all n. And because f and z is given by this quantity, we can absorb the minus 1 to the n along with the minus in the minus t to the power n and write the whole thing as t to the n by n factorial h and z times e to the minus z square. Now, I think you should be able to recognize where we are going, because if you look at this part alone, you will see this is exactly what the generating function was equal to. But that means our sum, which is a power series in t, but with coefficients which are the Hermite polynomials h and of z, is simply nothing but e to the z square times f of z minus t, or e to the z square into e to the power minus z minus t whole square. And if you just expand this out and use elementary algebra, you immediately arrive at this result. It is a 2tz minus t square, which is nothing but z square minus z minus t whole square. When expanded in powers of t, gives you h and z by n factorial as the coefficients. So this is how you actually arrive at a proof that the generating function for the Hermite polynomials is this particular function. Now, the connection between the Rodricks formula and the generating function is important enough that it warrants one more derivation. And this time, I'm going to give you a derivation which uses complex analysis. I have another motive behind that. Complex analysis and its methods are going to be very, very important in several of the derivations for the rest of this course. Take this more as a warm-up exercise for that. What we are going to use here is something called Cauchy's integral formula. Now, since Cauchy's name is connected to so many things in complex analysis, it may be a bit confusing as to which exact result are we talking about here. Let me remind you of that. Cauchy's integral formula essentially goes this way. It starts by assuming that f of z is analytic in a neighborhood containing a disk mod of z minus z0 less than r. That's just the entire disk, an open disk of radius r centered at the point z0. So we are talking about a function which is analytic in a neighborhood which contains the disk inside it. And if gamma is the circle, mod z minus z0 equal to r traverse counterclockwise. So basically what we are talking about is a situation like this. Z0 is a point somewhere in the complex plane, and we are talking of a circle which goes round the complex plane of some radius r. So mod z minus z0 equals r is our contour gamma, and that contour is contained in some neighborhood, and our function f of z is analytic everywhere in that neighborhood. Strictly speaking, I should be using the word holomorphic, but as anybody who has studied a bit of complex analysis knows that holomorphic is essentially equivalent to analytic in complex analysis. And moreover, it's possible that you may not even have heard the word holomorphic used before. Analytic will do for the time being. Now, if this condition is satisfied, that is, my function f of z is analytic everywhere inside this green neighborhood which contains my circle, then the nth derivative of the function at the center of the circle fn at z0 is related to the contour integral carried out over this contour gamma traversed counterclockwise of this function f of z by z minus z0 to the power n plus 1. There's an extra n factorial and there's a division by 2 pi I. So basically you can relate the nth derivative of the function at the center of a circle to the contour integral of a function carried out over a circle which is centered at that point. Now why is that of interest to us? Well, the nth derivative should be a clue, because remember, we already know that our h and z, apart from this factor of minus 1 to the n and e to the z square, is an nth derivative. So it's natural that a formula which gives us the nth derivative of a function at a point is going to be useful in finding out a relationship which involves Hermite polynomials. Well, let me just change our notation a bit. We are going to use x as the argument of the Hermite polynomial here, for the simple reason that we are going to still keep on using z for this variable of integration, which after all is a dummy variable of integration. So our z0 basically is this x. So h and x of course is this factor in green times this nth derivative. So what I'm going to do is I'm just going to replace the nth derivative of e to the minus x square using the Cauchy integral formula by a contour integral. Of course, this contour integral is being done over a circle of radius r centered at the point z equal to x. Now, what is the radius of this circle? Frankly, it could be any finite value whatsoever, because remember, all we demand is the function which is sitting in the numerator be analytic inside the circle and inside a neighborhood which contains the circle. And frankly, e to the minus z square is an entire function. It doesn't have any singularity anywhere on the finite part of the complex plane. So any radius will do. But anyway, what we have done is simply we have picked any such radius and replaced the nth derivative which is occurring in the Rodricks formula for h and x by this contour integral, which Cauchy integral formula assures me is the nth derivative. But then what we will do is we are going to find out this sum from n equals 0 to infinity of h and x to the n by n factorial. If you do that, notice that your sum n equal to 0 to infinity can move inside the integral. Of course, this n factorial will cancel with this n factorial. We still have the e to the x square and 2 pi I outside. And instead of multiplying by t to the n, I've just taken the minus 1 to the n inside the sum. Of course, anything which depends on n has to be inside the sum. So you get minus t raised to the n and then minus x to the power n plus 1. E to the minus z square is inside the integral, of course, but it's really not part of the sum, because, or can be moved out of the sum, because the sum is only over n. basically what has happened is that this thing written in orange here is an infinite sum, which if you look at it a bit, you would know that is something which you can easily figure out from class 12 algebra. There's nothing but an infinite geometric series whose sum is simply 1 by z minus x. That's an extra factor of 1 by z minus x as the first term, the n equal to 0 term. And the common ratio here is minus t by z minus x, so you just use that. A divided by 1 minus r, that's the formula we have used here. Of course, all the rest of the factors are just as they were. But now this sum is very, very simple. We have already carried out the sum. You can simplify it a bit further and write this as z minus x minus t. So now what happens is that my contour, which has a large radius, now has a singularity inside. The singularity is at x minus t. So we can now simply use the Cauchy residue formula, another of Cauchy's masterpieces, to simply evaluate this integral. Remember, the e to the minus z square here has no poles inside the contour, but the 1 by z minus x minus t has a single pole at z equal to x minus t. So all you need is a residue of this function at z equal to x minus t, which is trivially found by replacing the z here by x minus t. Remember, this is simple pole of order 1, and all you have to do is multiply this by z minus z0, z0 being x minus t, and taking the limit as z goes to z0, which will simply give you this thing. Of course, the integral is 2 pi i times the residue, and that cancels out the 2 pi i here, and you are left with this sum as simply it is a x square minus x minus t whole square. It is a 2tx minus x square. So what we have seen is n equals 0 to infinity, h and x t to the n by n factorial is simply this function, which is of course our generating function for the Hermite polynomials. Now that we have convinced ourselves that you can derive the generating function starting from the Rodricks formula, let us make use of this generating function to derive some interesting relations. We will start with recursion relations similar to the one we have already derived using the Rodrix formula directly. Well, for this, what we will do is we will start by labeling the generating function obviously as g for generating, of two variables t, z, and this of course is a defining property for the generating function. What we will then do is we will differentiate both sides of this expression with respect to z. If you do that, the left hand side of course is a known function of z, so it's pretty easy to differentiate. All that's going to happen is 2t is going to come down, and you're going to get the exponential, which is gtz times 2t on the left. On the right, of course, in fact, there's a partial derivative with respect to z that we are carrying out here. So the partial derivative, of course, will only act on h and z. So you will end up with h and z's derivative, h n prime z. T to the n by n factorial will stay as it is. The trick now is to actually realize the gtz, of course, is this power series. So we plug that in, and that tells me that the left hand side becomes a power series but with power t to the n plus 1, and that has to be equal to this power series on the right hand side. In order to compare terms in the power series, we need them to have the same index, which means I have to bring this n plus 1 down to n. But we know how to do that. We have already done that several times before. So what we will do is we will change n plus 1 to n, which will tell us that this hn will become hn minus 1, the n factorial below will become n minus 1 factorial, and the limit will start from 1 to start and go from 1 to infinity. So what does this tell me? First of all, it trivially tells me that there is a t to the 0 term on this side and there is no t to the 0 term on the left, which means that the coefficient of the t to the 0 term must be 0. But that's trivial because this is only telling me h0 prime of z, derivative of the 0th Hermite polynomial, which by the way is equal to 1, as you all know, has to be 0, which is of course a trivial statement to make. But what is non-trivial is that for all n which is 1 and above, we have this result. Hn prime z, the coefficient of t to the n by n factorial on this side, must match the coefficient of t to the n by n factorial on this side. But just to remind you, what we really have is 2hn minus 1 by n minus 1 factorial, which is the coefficient of t to the n on the left, must equal hn prime z by n factorial, which is the coefficient of t to the n on the right. And since n factorial is n times n minus 1 factorial, you have an extra n as a result. So hn prime z is twice n times hn minus 1z. So hn happens to be an nth order polynomial whose derivative essentially is n, apart from an extra factor of 2 here, times the previous order polynomial. So basically you have a sequence like this. Basically we have a polynomial of degree n whose derivative is essentially n times the n minus 1 z times some factor here. Lambda has been used too often in this lecture, but this lambda here just stands for any number, in this case just 2. Now, sequence of polynomials which behave this way, so that the next order polynomial's derivative, which of course is a lower order polynomial, is simply proportional to the polynomial of the previous order times n, are called Appel sequences. And what this demonstrates is that the Hermite polynomial is a special case of what is more generally called an Appel sequence. We will not go deeper into the theory of the Appel sequences and their corresponding umbral calculus here, because that would take us too far afield in the theory of special functions and polynomials and so on. But this recursion relation in particular is pretty interesting. In fact, you already know a very, very simple polynomial which does obey a relationship like this, where the derivative of the nth order polynomial is n times the derivative of the lower order polynomial times a number. And that is nothing but x to the n itself. The derivative of x to the n, remember, high school calculus, is n times the next polynomial, x to the n minus 1. So Appel sequences are really generalizations of nothing but simple powers of x. And Hermite polynomial happens to be one such. The previous recursion relation was derived starting from the generating function and differentiating both sides partially with respect to z. It's obvious that we can also partially differentiate with respect to t. And if we do that, the left hand side again returns the exponential. That's a beauty of having an exponential function. No matter what variable you differentiate it against, you essentially get the exponential function back. But if you are differentiating with respect to t, you are going to get 2z minus 2t as a factor in front. So basically, this differentiation is going to give us this result. Twice z minus t by differentiating the exponent here times gtz. On the right hand side, of course, the n equal to 0 term will simply vanish because n equal to 0 term does not have any t in it. It's just t to the 0. And for all other n's, what's going to happen is h and z will stay intact, and we will just use the property of the polynomial of the power n, which we knew from childhood or from class 12 or even earlier. But we have just seen that that's a property of an Appel sequence. We're just going to use that and just use the fact that the derivative of t to the n is n t to the n minus 1, and n cancels the n factorial to give you an n minus 1 factorial. By now you should know the drill. On the right hand side you have power series in t. The left hand side also is a power series in t simply by replacing gtz by hn here. Of course, this 2z and 2t breaks it up into two pieces. One piece has t to the n. The other piece has t to the n plus 1, which is just this outside t multiplying the t to the n. So what is left is simply to bring everything back to the same power. Of course, these two terms, this term needs no work. This one, you do need to work here. N has to rise by 1. So this becomes hn plus 1. This becomes n factorial. And instead of being from 1 to infinity, this series now is from 0 to infinity. You have to also change this n plus 1 to t to the n, which I have done in the next step. So this is what you are going to get. And if you just take the coefficient of t to the n on both sides now, and of course you can do this only for n equals 1 and above, because that's the only common range of the three sums. For n equal to 0, you simply get 2z h0z is equal to h1z, which again is trivial because we know h1z is 2z and h0z is 1. So this is trivial, but the non-trivial result that you get is valid for n greater than or equal to 1. That's hn plus 1z, the coefficient on this side, is 2z hnz, this coefficient, minus twice n hn minus 1z. Of course, the n comes in because of the cancellation between the n factorial and the n minus 1 factorial. So this is another recursion relation that I get starting from the generating function, but this time differentiating with respect to the other variable. So by using the generating function, we have managed to find out these two recursion relations. The first one relates the derivative of the nth order Hermite polynomial to the n minus 1th order Hermite polynomial. The next one is a connection directly between the Hermite polynomials of different order themselves. So you can actually find out any order Hermite polynomial by using this starting from the two previous order Hermite polynomials. Now, you can easily see that by replacing this 2n hn minus 1z sitting here by the hn prime z, which is the first recursion relation gives us, we will find this relationship, which of course is no surprise. It's a result we had already found out earlier, starting from the Rodricks formula. So the n plus 1th order Hermite polynomial is related to nth order Hermite polynomial minus hn prime z. Now this actually is very, very useful. This connected with this result is actually very, very useful to show or to convince ourselves that the polynomials that we are getting by using the Rotrix formula or by using the generating function are actually the same polynomials which satisfy the Hermite differential equation. So what we are going to do is we are going to use these recursion relations to show that h and z actually obeys the Hermite equation. But the Hermite equation, of course, is a second order differential equation, and we have only one derivative here. But the way out is simple. We just differentiate this once again. So we get h prime n plus 1 is twice h and z plus 2z hn prime z minus hn double prime z. So that's all you get by differentiating. But now h prime n plus 1z, according to this recursion relation for the derivative, is simply twice n plus 1 h and z. So you just put that in. And now we simply cancel out the 2h and z here with the 2h and z that I will get from this term. Bring everything to one side and we see that h and z obeys this second order differential equation, which is the Hermite differential equation. Of course, we wrote this as lambda minus 1 initially, but lambda is 2n plus 1 for integer n for the cases that we are interested in. So the Hermite differential equation is being recovered for the hns. So hns are obviously polynomials. The Rodrix formula should have convinced us of that. So hns are polynomial solutions to the Hermite differential equation. Now we do know that Hermite differential equation, being a second order differential equation, has two independent solutions. But we also know this. One of those solutions is a polynomial. The other one is an infinite series. Here, our hns, the ones we get from the generating function, are polynomials, so they have to be the polynomial part of the solution. So our generating function coefficients are polynomial solutions to the Hermite differential equation. So they have to be what we call the Hermite polynomials. You may have spotted that there is a gap in the argument there. All we can say is that they are proportional to the Hermite polynomials up to a constant. But we can always choose that constant as part of the definition of the Hermite polynomials, and we are doing it in such a way that whatever comes out of the generating function, that coefficient of t to the n by n factorial is what I am going to call h and z. Of course, you have seen that the Rodricks formula and the generating function were giving me the Hermite polynomials for small n, but this argument here should convince you that this really works for all n. But this is not the only reason why the generating function is useful. In fact, let us just try to see what else can you use the generating function for. One very simple use is in deriving what are called orthogonality relations or orthonormality relations for the Hermite polynomials. So if you just write the generating function, this is g tz, and we have just written the generating function once again here, but with t replaced by s. And of course, what I can do is I can always change the dummy variable of summation from n here to m. Okay, nobody can prevent me from doing that. Now, if you just multiply the two together, and that is precisely why I have changed the dummy variable, because I'm going to multiply them together and I don't want n to be confused with m. What I'm going to get is this expression here. It is a 2t plus sz, which is just this time this plus this, minus t square minus s square, which is what you have in the exponent here. And the sum becomes a double sum over both m and n of hmz h and z times s to the m t to the n by m factorial n factorial. What we are next going to do is interesting. What we are going to do is multiply both sides by e to the minus z square. So we are going to put that on both sides. And then we are going to integrate this result from minus infinity to plus infinity. So if you do this, the right hand side, of course, can simply be written down as a result of doing the integral first and then doing the sum. The integral is only over z, so the only z dependent terms are this one, the hmz, h and z, and of course the measure dz. So this is the integral that you have to do, and then you have to multiply the result by s to the m to the n by m factorial n factorial and sum up over all m and n. Fine, but what do you know about the left hand side? The left hand side is an integral which is pretty easy to do. If you just supplied an extra 2st here, then this would simply be nothing but z minus t minus s whole square in the exponent. Of course, that means you have to pull an extra e to the 2st outside. But now this integral is something you all know how to do. This is a standard Gaussian integral, and its value is simply root pi. So this double sum over m and n of this integral of product of hm and hn with a weighting factor of e to the minus z square turns out to be root pi times e to the 2st. And why is that useful? Well, this expression is a double power series in both s and t. So if we just write this expression here, which is a function of s and t, we should be immediately able to read off the value of the coefficients from which we should be able to read off what this integral is going to be. In fact, even without doing anything further, I can immediately see that since e to the 2st is a function of the product st, if you expand this out using the standard exponential expansion, you're only going to get equal powers of s and t. And what that means is, on this side, unless m and n are equal, you must have a zero coefficient, which immediately establishes our orthogonality result that e to the minus z square hmz h and z dz integrated from minus infinity to plus infinity vanishes whenever m is not equal to n. Why are we calling this orthogonality? A, because it's actually related to the kind of orthogonality that we know of in quantum mechanics, But more importantly, because this is a kind of inner product where you multiply two functions together, multiply that product by a weighting factor and then integrate. How did we know that e to the minus z square is the correct weighting factor to choose here? Let that be a mystery for the time being. We will later see that the whole theory can be derived or can be sort of understood starting from the way in which we define inner product properly. This will take us to the theme of Sturm-Liouville equations, which is very, very important simply because not only is the Hermite equation an example of Sturm-Liouville equation, but almost all the important equations we ever meet in quantum mechanics, almost all of them, are examples of the Sturm-Liouville equation. So we will discuss the Sturm-Liouville equation in some detail, and there you will see that there is no mystery really about this e to the minus z square factor. It comes out naturally from that theory. For the time being, let's take it as a given. After all, it is easy to see that this function wouldn't have converged if we were to integrate it from minus infinity to plus infinity by itself. You need a dominant exponential which brings the function down in order to make it converge. So for the time being, it's actually quite easy to understand why we need the factor of e to the minus z square here. Without this factor, the part in orange would not have converged over an infinite limit from minus infinity to plus infinity. E to the minus z square dampens the function enough to give you a convergence. Not only does it damp it out, it actually makes the integral very easy to express in terms of a known result and work it out. Now, if you look at the result, you can use it to figure out not only the fact that when m is not equal to n, this integral is going to vanish. You can easily find out what happens when m is equal to n. For that, all you need to do is write this side, which is root over pi e to the 2st, as root pi 2 to the n s to the n t to the n by n factorial. I decided to be a bit clever here and write this single sum on the left as a double sum over both m and n, and break up this s to the n t to the n into s to the m t to the n. But we have forced the m and n to be equal here by putting in a Kronecker delta symbol, delta mn. That's a bit of extra jugglery which you did not really have to do, but it sort of neatly tells you that the coefficient of s to the m to the n on both sides must match, and then this ends up giving me this simple result for the integral e to the minus z square hmz hnz dz is simply root pi 2 to the n factorial delta m, and this n factorial simply comes in from the fact that you really had an n factorial square for the terms where m and n were equal on the left hand side in the denominator, and you have a single 1 by n factorial on the right hand side. So you end up with an n factorial in the numerator. So this is the orthogonality relation for Hermite polynomials. In fact, it's more than the orthogonality relation. It's actually the orthonormality relation for Hermite polynomials. And when you are going to use it in quantum mechanics to talk about properties of the simple harmonic oscillator, this e to the minus z square factor becomes a very natural thing to talk about there, because remember, our wave function psi of z actually comes with an extra factor of e to the minus z square by 2 and the Hermite polynomials. So when you multiply two different wave functions, for example, and integrate to find out, say, expectation values or matrix elements, you will naturally get an extra factor of e to the minus z square, e to the minus z square by 2 from each one. To quickly summarize, this lecture has been primarily about the mathematical properties of the Hermite polynomials. There has been rather little amount of physics in the discussion in this lecture, but we have really established some very important mathematical properties which will be useful for physics in general and quantum mechanics in particular. In the next lecture, we are going to apply some of these results that we have derived in today's lecture to quantum mechanical problems. But more importantly, we will be concerned with describing the general theory of Sturm-Liouville equations. That's a huge topic, so we are just going to use that part of the theory that is going to be useful for us. But this will help us not only to understand, for example, where this particular Rotrix formula for the Hermite polynomial came from, but it will help us tie together various different mathematical functions that we will have to use in quantum mechanics from time to time and understand their properties in a sort of generalized way.